Hello students, this is Dr. Vantari Siva from Seekers. We are going to have some set of videos which covers the important concepts and topics of related to CBSE level. If you follow them, you will be able to cover minimum 60 to 70% of marks in CBSE level exams. If you want to have some tests on these topics, you can reach out to us to the number given below in the description. Okay, let us get started with the current electricity. Right. What is electric current? Electric current is nothing but, essentially, if you are talking about electric current is represented by I, how much charge is flowing per unit time through a cross section. For example, if you talk about a wire or a conductor whose cross sectional area is A, let us say, within this cross sectional area, how much charge is flowing in a given time t is nothing but a current. If you are talking about a small amount of time dt, how much charge is flowing in that small amount of time is nothing but a instantaneous current. Now if you are talking about a large duration of time, for example, it is delta t, which is large duration of time within which, let us say, delta q amount of charge is flowing through it. Such current is known as average current. So this is about your electric current. Now let us talk about the dimensions and units of it. Current I is equal to charge per unit time. So charge is having units of coulombs. How many coulombs of charge is flowing in 1 second? For example, 1 coulomb per 1 second is nothing but your ampere, 1 ampere. Okay, that's what is a unit of electric current. Now let us talk about what is dimension of it. So electric current is one of the fundamental physical quantities, hence the ampere is a dimension of it. Now let us talk about types of currents. So we have got two different types of currents in our syllabus. One is, if suppose current as a function of time, if I just look at it, if current is a constant, we can call it as DC. And if current is changing its polarity like this, for example, every regular intervals of time, or maybe like polarity is changing from positive to negative and so on, we can call such current as alternating current. We also have variable currents and pulsating currents, which is not in our syllabus. Essentially, direct current is the current which does not change its polarity, whereas alternating current is the one which changes its polarity in as a function of time. So that is what is called types of currents. In our syllabus we have got only these two, right? Yes. Now direction of electric current. So essentially, in a conductor of cross section A and length L, let us say if electrons are flowing in a conductor, then we consider that convention is electric current is in the opposite direction, whereas if positive charge is moving in one direction, we consider that current in the same direction. This is the convention that we need to follow. Okay. So drift velocity. What is the drift velocity? Drift velocity is nothing but, if you just talk about the electric current, how do we get electric current in a conductor? For example, if you just connect this conductor to a cell, what is the role of a cell? Cell generally pushes the charge carriers which are there in the conductor. For example, in a conductor we have got nearly 10 power 23 electrons per unit volume. So all these free electrons will be able to move as soon as they are experiencing some kind of electric field. Now if I am connecting this to a cell whose EMF is, say, V, higher potential plate will have V potential, lower potential plate is having 0, let us say. Then here V is the potential, means everywhere in this wire the potential is V, and here it is 0, means till here it is 0. You can see that from here to here, throughout the length of this conductor, potential is decreasing. We know that in the direction of electric field, potential decreases. Otherwise, potential is decreasing from V to 0 here. That means electric field should be there in this direction. This is the direction of electric field. You know that the force, electric force F is equal to QE. If electric field is in one direction, force will be in the same direction if Q is positive. If Q is negative, let us say, then what happens? Electric field will be in one direction. The force experienced by these charged particles will be in the opposite direction. Here you can see electrons are having negatively charged. Hence, they will experience a force in the opposite direction to this electric field. I hope you can see that. Now all these electrons will be drifted with certain velocity. That velocity is nothing but a drift velocity. The average velocity obtained by these electrons because of such external electric field is nothing but a drift velocity, isn't it? So what is this drift velocity? Let us see. Initially, inside a conductor, all these free electrons move very randomly in all possible directions. So what happens if you talk about average velocity of all these molecules will come out to be 0, because if suppose one particle is going with velocity u1, other particle is going with another velocity u2, and so on, then n number of molecules are traveling with velocity un, the net velocity or average velocity will be going to be 0. Why? Because if one electron is going this way, there will be one electron for sure which goes in the opposite direction. Hence, average velocity without external electric field becomes 0. Okay. Now, if you see the acceleration experienced by these electrons, let us see how do you get this. So you know that electric force F is equal to minus EE. I am talking about the magnitude right now. Magnitude right now, 1 minute. So magnitude, then this minus will become plus. Okay. So whatever. So here you can see that if I take F is equal to ma, if I equate it to this electric force, then acceleration experienced by electrons will be nothing but E by m. That you can see, if electric field is in one direction, acceleration will be in the opposite direction as per our definition for electric force, right? So if I talk about only the magnitude, acceleration is nothing but E into E by m. Okay. Now you can see that electric charge, mass of electron, applied electric field, all these three things are actually constants here. That means acceleration is a constant. Very good. Now if acceleration is constant, we can apply equations of motion. Let me apply first equation of motion. V is equal to u plus at. Now what is V? Final velocity. Initial velocity is u, let us say. Acceleration is a. Now you know that initial velocity is 0 and acceleration is what? A E by m into t. Of course, if I talk about its direction together, then average velocity, final velocity will become E t by m. Now here if you talk about t is equal to tau, which is called relaxation time. What is relaxation time? Relaxation time is the time between any two successive collisions. Okay. So for example, if electron is going and hitting with another electron and so on, how much time it has taken from this collision to another collision. Such time is nothing but relaxation time, right? So if I write that E tau by m, I am worried only about the magnitude, hence it will become drift velocity. Drift velocity Vd can be written as E tau by m. Right. So this is the expression for drift velocity. Okay. What is mobility? Let us understand this. Mobility is represented with mu. Mu is nothing but how much is the drift velocity gained by this electrons or charge carriers in a conductor because of external electric field per how much electric field you are applying. That is your mobility. So you have seen that what is the drift velocity? That is E tau upon m divided by E. This E that E gets cancelled. So it is E tau upon m. So this is the mobility expression. Now you can see that even though it is defined as how much is the average velocity or drift velocity per unit electric field, it doesn't depend upon these two factors. It depends upon this mostly and charge of the particle and mass of the particle and so on. Okay. So that's what is mobility. Let us see the relationship between current and drift velocity right now. Let us take a conductor. Now in time t, let us say in time t, how much volume has been covered by these electrons. Let us talk about here the volume. Volume is equal to, can I say it as area into length. So I am talking about a small length part, let us say, within which in time t, let us say it is covering the length L, and that length L can be written as a velocity into time, Vd into t. So area of cross section is A, and length is nothing but a Vd into t. This is nothing but your volume that is covered in time t. Now if you look at the number of free electrons per unit volume, number of free electrons per unit volume is this. Now if I want to talk about total number of free electrons, that's equal to n into V. Okay, so here what is this n? So what is the volume V? Volume V is equal to A into V dt. Now the total charge that is flowing within this volume is equal to like you know, charge is quantized, the total number of electrons times its charge of each electron. So what is this capital N now? Na Vd t into E. Now you can see that charge, I am taking this time to this side, charge per unit time is nothing but electric current, okay, and that's equal to NAE Vd. So you can remember it like NAE Vd, NAE Vd. So what is N here? Number of free electrons per unit volume. What is A? Area of cross section. E is nothing but a charge of electron, and Vd is equal to drift velocity. So that's the relationship between your current and drift velocity. Now if I write current per unit area, I am taking this area to the other side, then I get NEVD, and this equal to current density. Okay, so current density J is equal to NEVD. This is the relationship between drift velocity and current density. Right, now let us talk about Ohm's law. So just now we have seen that you can see J is equal to NEVD. Let us take that. J is equal to NEVD. Okay, so what is this Vd? So you have seen that drift velocity Vd is equal to E tau upon m. Now I can say that it is NE square tau upon m into E. So this can be written as basically a conductivity. Conductivity sigma, that's equal to NE square tau upon m. Now if I write this, J is equal to sigma E. Okay, so what is this J? Current density, that's equal to sigma into electric field. This is called Ohm's law. Of course, Ohm's law in the form of vector, or vector form of Ohm's law. Clear? Now we already know that V is equal to IR. Of course, we can derive it from this. Okay, let's not waste our time anymore on that. But anyway, what is V here? How do you get that actually? Essentially, inside a conductor, more is the potential difference that you are creating, that will be able to create more current in a conductor. So V is directly proportional to current. Now here you can say that if I remove this proportionality constant, I get R as a proportionality constant. That's how you can understand this Ohm's law. Now what is this R? R is nothing but electrical resistance. Electrical resistance is nothing but, this is the opposition offered by a conductor to the flow of charge carriers. Okay, that is your electrical resistance. Now let us discuss about the details a little later. And now what is this the conductors which follow this Ohm's law are called ohmic conductors. The conductors which follow Ohm's law is called ohmic conductors. So the graph of voltage, current as a function of voltage will be a straight line like this. Now whereas the conductors which do not follow Ohm's law are called as non-ohmic conductors. Now the graph won't be linear, but it will be non-linear. It won't be a straight line. It can be of something like this and so on. Okay. Now let us discuss the factors on which the resistance depends. Now you can see inside a conductor, what we have discussed about resistance right now. Resistance is nothing but the opposition offered to these charge carriers inside a conductor. Now here, if length of a conductor is say L, more is the length, more is the resistance. That means what? Resistance is directly proportional to length, and it also depends upon area of cross section. So here less is the area of cross section, more is the resistance. So you can say that R is inversely proportional to area of cross section. Now if I combine both of them, I get L upon A. If I remove this proportionality constant, I get R is equal to rho L by A. So what is this rho? What is this rho now? Rho is called resistivity. Resistivity. Okay. So resistivity is dependent on or depends on material. So for a given material, it is constant. We will discuss about the details in the next slide of resistivity. Now you can see that, so R resistance for a given conductor or resistor will be keep on changing depending upon its length or maybe area of cross section, and also rho. Okay. So if suppose if you are taking a thin wire, so area of cross section will be less, then resistance automatically increases. Now if you are talking about area of cross section is large, then resistance decreases. Opposition offered by the metal or conductor decreases. Now if you talk about length, if length increases, resistance increases, whereas if length is decreasing, automatically resistance will be decreasing. So that's how resistance will be depending upon such factors. Now let us see, resistivity also is not a constant for all circumstances. It may be the same value for given conductor, but then it is not same for all the cases. Now let us see, we just have seen from the previous slide, sigma is equal to n E square tau upon m. So what is resistivity right now? Resistivity is nothing but reciprocal of conductivity. So if I write that here, it is n E square tau upon m. Clear? Now you can see that mass and charge does not depend upon external factors. Now if you see, it depends upon the temperature. For example, if temperature increases, then what happens? If n may be increasing or decreasing or whatever, tau also may be like increasing or decreasing on several factors. Now let's talk about first of all, if you see this, if n increases, rho will be decreasing. If tau increasing, rho will be decreasing. Of course, other volta also is right. I mean, vice versa is true. For example, if you see, if temperature increases, in the case of conductors, let us say, I am talking about the conductors. Inside a conductor, we have got a very large number of free electrons. For example, in the order of 10 power 23. Now, if you are increasing this temperature, then ionization will happen. Ionization will happen. Because of ionization, what happens? Number of free electrons increases in a given volume. But then, what about tau? Tau will be, what is tau actually? Relaxation time. So here, as soon as the temperature increasing, then vibration increases. Then what happens? Automatically the time for which relaxation happens is less. Tau will be decreasing. Now you can see that both of them, both number of free electrons per unit volume and tau are in denominator. If one is increasing, other one is decreasing. So here, in the case of conductors, such increase, maybe like even though number of free electrons are increasing, our increase doesn't matter much. This change is small compared to this. So this effect will be dominating in the case of conductors. Then what happens? Rho will be depending on tau for the case of conductors. So here, when temperature increasing, tau is decreasing. Tau is decreasing means automatically rho will be increasing. So let us see, the graph. The resistivity as a function of temperature will be increasing like this. That's how you get the graph for conductors. Now let us see now. So in semiconductors, you have just seen that rho is equal to m by Na square tau. Now you can see here in the case of free electrons, in the case of semiconductors, number of free electrons per unit volume is not that much appreciable. Now you can see almost negligible. If because of ionization, what happens, this n will increase and tau will anyway decreasing, but this number will be very large, or you can say this is dominating factor compared to this effect. So hence when n is increasing, rho will be decreasing. So in the case of semiconductors, resistivity will be decreasing as a function of temperature. Resistivity as a function of temperature, you can see that resistivity will be decreasing like this. Okay, so this is what we call it as a negative temperature coefficient of resistance. Because of this property only, we use the semiconductors in our daily life applications, for example device applications. Okay, and in the case of previous thing, that is conductors, we call it as a positive temperature coefficient of resistance. What does that mean? The slope is positive here, hence it's called positive, and that means when temperature is increasing, resistance also increasing. That's what is nothing but positive temperature coefficient of resistance. But here when temperature is increasing, resistivity is decreasing, okay, as a function of temperature. That's why you call it as a negative temperature coefficient of resistance. Okay, so we are going to see the remaining parts in the next video. Thank you.